Hello, everybody. Good morning, good afternoon, good evening, wherever you are in the world, and welcome to our presentation today on Kubernetes in the Cloud Part 2. This is being presented through the SNIA Cloud Storage Technologies Initiative, which I'm going to tell you more about. And I'm going to go now over to just introduce everybody who's going to be covering this material today. So first of all, my name's Michelle Tidwell. I'm Program Director and Global Offering Manager for Software-Defined Storage at IBM. And with me today, I have two colleagues, Matt Levan, who's an IBM Storage Solutions Architect, and Tom Clark, IBM Distinguished Engineer and Chief Architect of Storage Software. So we're really happy today to be here to share with you some information on Kubernetes and hybrid cloud. And just to go through some legal stuff, this is a SNIA presentation. The materials contained in this presentation are copyrighted by SNIA. If you will get copies of this in a PDF at the end of the webcast, so feel free to download that. You can use these as long as you use the information in its entirety and use it at your own risk. There are no warranties or anything implied. So now that we're through all of that, just a few words about the Storage Networking Industry Association, in case you don't know about it. We're a group made up of 185 industry-leading organizations around the world. We have about 2,000 active contributing members, and we service about 50,000 IT end users and storage pros worldwide. So it's a very big organization. If you'd like to know more about it, or if you'd like to join SNIA, please do visit our website. We'd love to have you. And as part of SNIA, we have a group called the Cloud Storage Technologies Initiative. And what we do is the type of thing that we're doing today, which is educating vendors and users on cloud storage, on data services and orchestration software, and really helping to support and promote business models and architectures around the, very hot technologies that are available today, like OpenStack, Kubernetes, object storage, anything to do with cloud or hybrid cloud. So hopefully this will be useful for you, and stay tuned for more that we'll be bringing to you on these subjects. Okay, so without further ado, let me just introduce the agenda we're going to be covering today. We're going to start with a conversation about the transition to a hybrid multi-cloud world, and Tom Clark's going to go through that with an introduction, and then Matt will take you through details on Kubernetes containers, container-ready storage, as well as the new container storage interface, and we're going to have an actual demo that Matt will take you through. Please feel free to type in questions during the webinar. I'll be monitoring those. We'll try to keep it interactive to answer them as we go along, and hopefully we'll have time to cover more Q&A at the end. Okay, with that, I'll just turn it over to Tom.
Thank you, Michelle. Let me just give you a little bit of introduction here and some of the evolution that we see in the environment, in traditional IT environments, and this movement to this cloud operating model. I think we're all familiar with the last number of years and the transitions that we've seen to public clouds, and that's becoming more complex. As you see in the picture here, it's not just public clouds. There are dedicated clouds being run by a service provider or a public cloud provider, as well as private clouds, as traditional IT environments want to take advantage of the same kinds of capabilities and advantages that a cloud operating model provides, the kind of flexibility, the agility, the services type model and self-service kind of model that a cloud provides. And so what we see happening in the industry is as traditional IT way of doing things shrinks, we see this uptake in these cloud models. Now, as IT environments evolve to these cloud operating models, we see two things happening here. One is that IT environments operate in a very hybrid kind of approach. So it's not all private cloud, it's not all public cloud, it's not all of any one thing. It's a very hybrid kind of an approach. So I have some private clouds, I have public clouds, and in fact, I have typically multiple public clouds as well. So it's a hybrid model and it's a multi-cloud kind of a model. Now, that presents some challenges. How do I manage this environment and operate it in a consistent kind of a way? How do I manage my data and the locations of my data, movement between these clouds as I have needs for the data and for various applications in different places, the connectivity aspects of it. And for us here, we're focused on the storage piece of that and how storage fits into this cloud model. And certainly Kubernetes and containers is very much in the middle of that. Now, let me talk a little bit about how this journey is happening and the role containers and this infrastructure. What we're seeing is, containers and especially Kubernetes, which is becoming kind of the de facto way to manage a container environment in the industry, becomes really has two main aspects that place it really at the core of this evolution to cloud. One aspect of it is just the operating infrastructure, and you see that on the right. In this journey to cloud, I have a cloud operating environment, yes, applications, data, the integration of all these pieces and management, but the foundational infrastructure and the providing of the services is very much being built on containers and a Kubernetes infrastructure. So as we talk about it in these sessions, and as Matt's going to take you through how storage fits into this container world, it's very important because this is the core infrastructure in these cloud environments and this journey to cloud. Now, the other aspect of it that's really important is it's also the modern application approach. Containerizing applications, creating microservices really is the modern way to build applications, as it provides a lot of agility, isolation of functions, ability to scale those different facilities and operations across a clustered environment and a wide environment. So as an enterprise tries to move into this cloud environment, they have traditional applications you see at the bottom of this chart. They may just want to migrate into there, what we call a lift and shift. Just let me operate it in a cloud model. In other cases, it's worth the expense to go ahead and modernize an application, start breaking it apart into microservices in this container model. If I'm building a new application, I'm going to build it with this kind of a containerized type microservices approach to things. And that all fits into how I'm going to manage this as well. So from the storage perspective, we're used to dealing with storage administrators, maybe VM administrators, as we think about plugging our storage into IT environments. Now we have some additional personas that we're going to be dealing with increasingly, and we see that on the left here. One that we're calling Todd, who's an operations person. They're operating the cloud. So they are trying to make sure that the services of the cloud and that cloud operating environment is available, is operating well. They're monitoring, they're managing that cloud infrastructure to provide those services. And the other person is Jane, who is the developer. So the DevOps type model, very rapid evolution of applications. Jane wants to leverage the services of the cloud, deploy my application, get the compute network and storage provided so that I can deploy my app, operate it, manage it, evolve it, those kinds of things. So from the storage perspective, we have to fit our storage into this container Kubernetes environment we need to provide automation and the services type operating model that's required in this cloud environment. So as we think about Kubernetes and containers, how storage fits in that environment and operates is very critical to our participation and our ability to support this journey to cloud. So I want to turn it over to Matt, because Matt is now going to take us through, how does storage work in this environment, how does our storage become cloud ready, and these interfaces and facilities that are available in Kubernetes to be able to plug in storage and operate it in this journey to cloud. So Matt, I'll hand it over to you.
All right, thanks, Tom. So I'm going to do a quick introduction to containers for anyone that wasn't able to see part one yet. It's a great webinar and should definitely check it out. But so containers, and even like if we go through the evolution that we've gone through, we, years ago would have bare metal servers and they would run an application and you would design around being able to handle peak workload of that application. But the problem was you had resources that were not being used, right? So came along virtualization, hardware virtualization. So that's where we got virtual machines. And we were able to make much better use of resources because not every application has the same, peak at the same time. So you were able to stack a lot more different applications into a single server. But the thing with hardware virtualization is you still need to have a guest operating system. So that comes with, it comes with the binaries, libraries, dependencies. It uses memory just for the kernel and different systems to operate. And another thing with virtual machines is you couldn't possibly run, you would kind of generally, again, run a single application had requirements for its binaries and libraries on a single virtual machine. You weren't able to really condense that even further. So one of the things that came along is operating system virtualization. So instead of having to virtualize the hardware anymore, now we're virtualizing the operating system. And Linux was a key part to that because it had, things in it like C groups and processor isolation that allowed to be able to start running, much leaner applications. And even better, you could run applications on the same host that you weren't able to run before because they're isolated. And with containers, they're very small. So, a virtual machine would be probably, 100 megabytes, a couple hundred megabytes, gigabyte, right? Well, now with containers, you can get down to as small as 100 megabytes. You can get really tiny. And another great thing with containers is the portability of them. Java was kind of this programming language that was always going to be portable. You can run it anywhere, build once, run anywhere. But didn't really come to fruition. But with containers, you can build a single container that works across multiple different architectures, multiple different operating systems, and run them truly in different places, which is great because all you do is you take the binaries and libraries that are dependent on that application and bundle it together into an image that you can upload to image registries and then deploy anywhere. So you get this true independence from, hardware. You can run essentially anywhere. But why is storage so important to containers? The thing with containers is, the portability and everything, it makes them great, but they're ephemeral, which means that, you might write some logs or data into your container, but if for any reason, maybe the lifespan of the container has ended, or, there was a fault and had to restart, or, you're just migrating it to another location, or which is a lot more common, is you're just upgrading the container or the software in the container. But you don't actually upgrade the software in the container. You essentially delete the container and create a new container. And as you can see on the left-hand side, if I were to write my database files into the container, and I were to upgrade from version 1 to 1.0 or 1.1, all that data would be gone. So that's where we need to bring in external storage to be able to keep that data through different life cycles of the application. You know, upgrade the application from version 1 to 1.1. You found a bug in your container that you need to deploy a new version. Lots of different reasons. So instead of writing data into your container itself, you're now accessing external storage from the container so that you can do this life cycle of containers. So Kubernetes didn't really start with storage in mind. Now it's developed up to 3 different types of drivers. The first one that started was in-tree drivers. So in-tree drivers mean that the storage driver is part of the Kubernetes project. So it was built, linked, compiled against a specific version of Kubernetes. So, you know, I think we're up to 1.15 now. So you would build it, you would, you know, essentially have to develop it for that version every time. But it became very difficult and challenging to add support for new volume plugins because you're tied to the release schedule of Kubernetes, which is quarterly, but you couldn't go out of schedule. You were, you know, dependent on the release. So if something changed between one release to another, you might have to make additional changes. Additionally, it was, you know, third-party storage drivers was causing reliability and security issues in core Kubernetes. So they moved away from that a few years ago, I think a couple years ago. And they have not accepted any of these in-tree drivers since Kubernetes 1.8. And any current in-tree driver is being migrated over to Container Storage Interface, CSI. I'll touch on that a little bit later. And then the next type of driver that they developed was flex volume drivers. So flex volumes are executable-based model to interface with drivers. So essentially, you would, you know, build your driver to communicate with Kubernetes, and you would install it on your nodes. There's a couple of different ways to do it. There was a master node one, and then there was ones where you just installed it on worker nodes. The difference was, though, that if you wanted to handle an attach operation and have the master handle that, you had to install your flex volume driver on the master also. And I'll go into more details on those type of operations next. But the latest and greatest thing, which just went GA with Kubernetes, I think 1.13, is Container Storage Interface. So the Container Storage Interface, or CSI, is a standard for exposing arbitrary block and file storage systems to containerize workloads on container orchestration systems like Kubernetes. So this was built as a collaborative effort between different container orchestration engines. So Docker was involved, Mesos was involved, Google was involved. So this was a collaboration that was done together under the CNCF, the Container Native Computing Foundation. So CSI is going to allow for, you know, third-party storage vendors to much more easily write code for Kubernetes without ever touching Kubernetes. And I'll go into a lot more details about CSI. So here are the basic storage operations that, you know, all the drivers essentially do, right? So the first is create, delete volume. So this is pretty, you know, self-explanatory, right? A request comes in to Kubernetes for a volume of a certain size. Kubernetes then passes it to the driver, and that driver then, you know, communicates to the storage array, and will create a LUN or a file system or a, you know, NFS share, whatever, you know, driver it's supposed to be doing. So it'll create that, and as part of the operation, it'll delete it when it's not needed anymore. The next is attach and detach. So again, or, you know, old school storage people will call it map, unmap the volumes. But again, so this here would, you know, either map the volume to a node in the cluster. So nodes are worker nodes. So that's where, you know, you're running your applications at. So it would map it to the appropriate node or map it to the whole cluster, depending on configuration of the driver. And then detach, unmap would, take it away once it's not being used anymore. And essentially, volumes are used when a stateful container is started. So you don't have to map it. You only map it when it's in use. So it's pretty handy there. And again, it can be handled by master or non-master nodes. And that's primarily around in case you're worried about node isolation or node going offline. Obviously, a node that's offline can't be responsible for unmapping a volume from itself. So a lot of drivers will use master-initiated attach-detach operations so that, hey, if you lose a node and you need to get that container back online, you're able to essentially delete the node from the cluster, and then it'll force it to detach and reattach to a new worker node. And then the last operation is the unmount or mount-unmount operation. So again, it'll once the new volume has been mapped to the host, it can be part of the rescan process to look for the new volume on the SCSI bus, or it could just mount, like for example, an NFS volume to a directory. And the kubelet is what's responsible for doing it. So kubelet's the binary on the or on the nodes that is responsible for the communicating to Kubernetes and doing the work there. So also some file systems will be responsible for creating a file system if it's a block device or just making it available. And then again, it'll be handled by it'll handle the unmount operation. So when a stateful container is done, it'll unmount it. So the one nice thing I'll say now about the CSI driver, there was very many different ways that drivers would mount a file system and set permissions, set ownership, different things like that. With CSI, Kubernetes has gone with a sidecar approach where every CSI driver will use this sidecar to handle the mount operation. So you won't get this inconsistency between drivers anymore. You'll get a unified approach, which is really nice. Now let's jump into the storage terminology specific to Kubernetes. So with Kubernetes, there's persistent volume. So this is the object in Kubernetes that describes the implementation of the storage. It's independent of any individual pod that uses the PV, and it can be either statically provisioned or dynamically provisioned. During the demo, I'll do both so you can see how that works. And then there was the persistent volume claim. So this is a request for storage by a user requesting a certain size and access modes. And the next slide covers access modes. But this allows the user to abstract storage resources with varying properties. So for example, I could, have as an administrator, have created 5 different persistent volumes out there that are ready to use by developers. And, they could have different varying properties, but the developer then gets to create the persistent volume claim, which will request that particular thing. So if I ask for a, read-write many of 20 gigs with a persistent volume claim, and the, administrator had created persistent volume for me, that claim would take ownership of that persistent volume, which is essentially binding them together. And that's persistent volume claims. And then the newest thing is storage class. So this is a way, again, of also, providing administrators the capability to give developers the storage of different classes. So I could have, gold class, which is for my production environment. I could have a silver class, which is for UAT, and a bronze class that's for, just the development. I could have, flash as my gold and spinning disk as my bronze for different use cases. But it allows for for mapping and giving developers that choice of what they need to use. With dynamic provisioning, the volume plugin, so example, Flex Volume, Entry, or CSI, will have a provisioner that defines which driver is going to fulfill that request. And for those with like the visual representation of this, which is me too, so I like to throw in like another way of displaying this here. So this is showing an example of essentially dynamic storage provisioning. So here I have a storage class named Gold with certain capabilities I've defined in it, and then my provisioner is a driver name. So a developer goes and says, I need a persistent volume claim named Mongo of some size for storage class Gold, and I'm going to make it read write once. So this is essentially going to be a block device, most likely. So my driver is then going to go create a persistent volume, which is a run on a storage device. And then once I create the pod or a container to use that, I would reference the persistent volume claim. You don't reference the persistent volume directly. Again, the claims are references to persistent volumes. So that is what I use when I do my creating a stateful container. So here's some information specific to volume. So there's 3 reclaim policies. Recycle has been deprecated. It's not used anymore. The recommendation is to use dynamic provisioning. It was unreliable. It didn't work all the time. Essentially all it did was remove any data on that volume, so it'd be made available for use somewhere else. But they found that it was just not reliable enough. So really the 2 are retain and delete. So delete is the default when using a storage class, and retain you can change to it whenever you want to. So say you have, if you were to have a dynamically provisioned persistent volume claim with delete, and I deleted that PVC, it would also delete the PV behind it. But if I set it to retain, it'll just delete the PVC, but the PV will become unallocated and available. And then we have the 3 different access modes. So there's read write once, you'll see it as RWO, read write many, which is RWX, and then read only many, which is ROX. So block is generally used for read write once. It can only be mounted by a single node and accessed by only a single node. But generally used for like databases or other things where you would use block storage. Read write many is something like, NFS, different, network attached storage where you can, amount it to different containers and it can write to it. You'll see a lot of times for shared logs, web files, AI, ML, DL data sets. So anything where you need containers to be able to access things differently. And then read only many, which would be something like static web pages that you're serving up and you don't want them to, any container to modify them, but you want, many different web servers to access them. So that's the use case generally there for read only many. So there's essentially 3 different types of storage that are used with Kubernetes. You have block. Again, good for read-write once, access mode. Could be used for read-write many if your application can keep consistency of any file system or whatever underneath of it. I haven't really seen that used too often, but generally I'll see like read-write or block being used for databases, etc. And then we have file, things like GPFS, NFS, or SMB can be used for read-write once or read-write many depending on use case. And then we also, have the same things here, logs, AI, ML, DL data sets. And last, which is not really part of Kubernetes use cases at this point in time, it's not part of construct in Kubernetes. You can't just provision like a bucket on an object store that you can use. Generally, accesses through like an S3 API that the application is using. So your container application would just write directly through the S3 interface to the object store. But there is a Fuse-based file system out there that allows you to essentially mount an object store as a file system to access that object store. And general use cases are going to be, images, documents, backups, things where object really shines. All right, so I'm going to jump into the container storage interface here. So as I mentioned, it's a standardized storage interface for core container orchestration systems. So Kubernetes, Mesos, Docker, and Cloud Foundry were all part of the development process. It makes installing very easy. So it's essentially just creating two different deployments within Kubernetes, very easy. Again, driven and specified by CNCF, the Cloud Native Computing Foundation, and CSI spec version 1.0 is what came in 1.13. What's good is, so Flex Volume and CSI can coexist in the same system. So again, the storage class provisioner defines what driver is used. So if you specify a Flex Volume driver, it would use that. You specify a CSI driver, it would use that. And the Flex API will be maintained for a while. So what is so important about CSI? It's that all future active development is going to be on that. So any new features that you're looking for that might not have been in Flex Volume, for example, most Flex Volume drivers did not have snapshot capabilities, didn't have the capability to clone, did not have the capability to do volume resizing. But these are all things that are currently in active development for CSI. So with snapshots, they went alpha in 1.13. They did not go beta in 1.15. So hopefully in 1.16, snapshots of CSI volumes will be beta then. They're working on capability to do cloning. So if you have a data set or a volume that you want to make a clone of, you'll be able to do it all through Kubernetes. You won't have to go to the storage and do anything there. You'll just be able to go into through Kubernetes, clone a volume, and start using it for another container. Something also very exciting is the topology-aware volume provisioning. Right now with Kubernetes, you can kind of label your nodes and say, I'm on the East Coast, so this is this, if I provision this storage class, it'll get defined there. And then I could have a West Coast storage class that has different node names, and I would have to do it. So it was a lot of, finicky stuff where you kind of had to self-define these things. But with CSI, they're going to become aware of the topology. So to know, hey, if I request storage in this location, it knows which storage to go talk to and create the volumes. And then again, something that has been asked for a long time is the capability to resize a volume. So you start out with a 20 gig volume you're just going to do testing with, and then you find out, oh wait, we're going to go, keep using this for other things, and we need to grow it. You didn't have the capability to do that with Flex Volume, and it's a pretty complicated thing because essentially you have to have, the intelligence to know what the file system is, how to extend the volume, and how to then resize the file system. So that's one of the things that they're working towards with the target GA at the end of this year. And something that's kind of new is raw block support. This is essentially where you just don't make a file system. The application is going to be responsible for creating that file system. So you would just map a volume out there, and the container will be responsible for what it needs to do next. So this is a picture of what the CSI plugin is going to look like. And as I mentioned, CSI is making use of sidecars. So specifically for Kubernetes, they're developing these different sidecars, and we'll be able to see kind of the objects they work with here. So, what the CSI plugin design goal was that your driver only needs to worry about storage operations. So creating volumes, mapping volumes, growing a volume size, snapshots, clones. The CSI driver does that stuff. You write your driver to do storage operations, and anything that doesn't really interact with the storage, there's sidecars to do that. So at the bottom we have a controller, and at the top we have a node. So the controller is essentially the one that's going to do all the operations around create, etc. And it has sidecars it's going to attach to. So the external provisioner is the one external provisioner is the one listening to the Kubernetes API for requests for PVCs. It knows about the storage classes. So it takes that information from Kubernetes and passes it to the plugin for the plugin to do the storage operation. You don't have to write a listener to listen for these things anymore. Now you just load in the sidecar. Again, same with the snapshots. There's going to be an external snapshotter when that comes around, and it'll listen for these different objects within Kubernetes. And then there's a register, so you'll tell Kubernetes, hey, this is my plugin name. When requests come in for this provisioner, you talk to me, essentially. And then we have the external attacher. So again, it's listening for the attach request from Kubernetes, and it'll send it to the plugin. And then we have the node plugins, which are essentially responsible for, listening for the attaches to occur, and then it'll do the mounting and all these other things here. So that's kind of a quick glimpse of what makes up CSI in Kubernetes. Mesos is going to have their own sidecars. Docker is going to have their own sidecars, but this is specific for Kubernetes. And here's just another kind of example of what it'll look like. What's important here is that you just have one CSI controller, and then you run a daemon set for your CSI node. So all the worker nodes get a CSI node installed on them so that they can handle the node operations. And you only have the one CSI controller that's handling the storage operations. So very simple, much simpler than you'll see later when I talk about flex volume. And so this is the kind of the new stuff around snapshots. So this is very new, so I'm not that familiar with it. I'm still learning myself. But essentially, it's going to take kind of the same approach that persistent volume claims did, persistent volumes did, and storage classes. So again, a volume snap is equivalent to like a persistent volume claim. So it's going to take this volume snapshot content. So what will happen is, you'll have a snapshot class, which will, define the parameters, kind of similar to like a storage class. But again, and we'll do this. So this is kind of all the new features that are coming with snapshots. And again, it'll be handled by the external snapshotter. So you don't have to write anything there from a driver's perspective. You just, have to handle being able to do snapshots on the storage device. So the thing with the volume snapshot content, so this is going to be information about the snapshot, the source, creation time, and the handle to it so that you can make use of it. So if you want to take a snapshot, mount it to another volume, run some, or another container, do some tests against it or ETL or whatever you want to do against that snapshot is there. But then also one of the things that came with this is persistent volume and use protection. So you might have a snapshot out there that you forgot about, and you're like, all right, I'm done with this persistent volume claim. Let me delete it. Well, there's protections against doing that. It'll warn that there's a snapshot in use, and you just can't delete the PVC yet. You'd have to get rid of the snapshot first. So that's a good saving grace there. All right. So I'm going to jump into flex volume. So this is where I'm much more familiar. It's been around for a few years. CSI is pretty new. But this is essentially the same thing that's going to happen for CSI. So again, we go back to, we have 3 standard operations: create, attach, and mount. So I'm going to kind of go through the process flow of creating a persistent volume with dynamic storage provisioning. So here I have, a Kubernetes provisioner, and I have Kubernetes flex volume drivers. Again, I'm doing, master node attach, so flex volume has been installed there and made available. So what happens is, developer requests a persistent volume claim for a particular storage class with certain attributes, so size, access mode, things like that. The provisioner identifies that that request is there, validates it's a good request, that you have the authentication to do it. The provisioner then passes that information to the storage device, and it'll create a volume. So in the case of a block device, it would create a LUN, and that information would be passed back to the provisioner, and it would create the persistent volume object for that newly created device, and it would be bound to the persistent volume claim. So if you look at the details of a persistent volume, you'll see information about, like, the worldwide ID most likely, or some other information that is that storage object that Kubernetes knows about. So the next thing is we need to make use of that volume. So we're going to create a stateful container. So what a developer does here again, so they're going to create a container requesting use of that persistent volume claim. With Kubernetes, there's a controller manager that's going to do with the master node attach. It's going to trigger the attach operation. So in this example, the last worker node in my cluster is going to be attached to. The next thing I do is it's going to again validate the request is available, and then I'm going to map that volume to that worker node. Once that mapping has completed, the node is going to do a rescan of this OS for block, and it'll find a multi-path device. And in this case, it's a LUN, so it's going to create a file system on it and mount it to a path. In this example, it's just /path worldwide name. It makes it pretty easy. And once that is done, the container, or there'll be a bind mount between the containers directory and the host directory that it got mounted to. So in the container, it'll come online and have access to the data, to that volume with the file system on it. So that's essentially the process that CSI is going to do. It's what Flex does. The difference will be you'll have a CSI controller doing all the operation, a lot of the operations. It won't be dependent on the master nodes. All right, so I am going to jump into a demo now.
While Matt switches to the demo, I just want to remind everybody that in the chat, please feel free to ask any questions, and we'll handle those along the way. Thanks.
All right, so here is a user interface. So here in this case, just going to change out here. So I have a flex volume driver installed and configured. And down here, I'm going to do kind of the first step, right? So I'm going to essentially create a persistent volume for using NFS. So I'm going to go up here to create resource, come down here, and go in here. So here I'm creating a persistent volume with NFS. So it's read write many, it's retain, and it's backed by this path here, in this server, and read only. So this is an example of essentially an in-tree provisioner. So it's not really doing any creation. This is and also it's static provisioning. So it's not going to go create the directory out of my NFS server. It's just creating the resource that can be used. So I'll do that. So here I have, type NFS, read write many, retain, and it's available. So the next thing I need to do to so that I can keep using this is I'm going to go over here, again, create a resource, and I'm going to paste in YAML. So this is, you can either use JSON or YAML. I'm more familiar with YAML, so I do this. So essentially I'm creating a persistent volume claim here with the same name as the persistent volume I created. But notice here, I'm not specifying anything. All I'm saying is the resource I want is 1 gig, which I also created the persistent volume as 1 gig. So here I'm going to go create and come over here to persistent volume. And you see here, my persistent volume claim is now bound to my persistent volume. So because that persistent volume met the requirements of the persistent volume claim that I created. So the 2 requirements I essentially gave it were access mode of read write many and a storage resource of 1 gigabyte. So this is now bound. So before it was available, but now it's bound. So the next thing I want to do, and this is a lot of text in here, so sorry, it's the easiest way for me to show creating a container. But here at the bottom here, so from this deployment, I'm giving a persistent volume claim here with the claim name of this. So I'm telling this resource that it's going to use this persistent volume claim, but then within my container, I have to tell the container where it's going to mount that data. So this name here is what is being used here to relate each other. So I'm telling this deployment that it's going to use this volume, and that in here I'm telling this container, this is the volume you're going to use and this is where you're going to mount it. So again, I'm going to hit create, and now I'm going to go over to my workloads and deployment. So I created a deployment. So here's my deployment I created, and here's the pod that's coming online. So I can jump in here and look at events, and I think I already had run this, but sometimes there would be an event that said, essentially this container has, done a NFS mount of that file system I gave it in here. So essentially that is, static provisioning and being able to go through using a persistent volume, claiming it with a persistent volume claim, and then making use of that persistent volume claim with a container. In this case, I just used the deployment because it's the easiest way to spin up a container. You can do it directly with pods and stuff. Yeah.
We do have a few questions that came in. Well, first of all, there's a question about providing a copy of these slides, and at the end of the webinar, there will be a URL broadcast to everyone to be able to download the slides. So the questions are, in today's environment for Kubernetes Flex storage, what is the suggested process to back up these stateful persistent volumes, or is that not necessary anymore?
No, you still need backup. So you can use many different ways. You could take snapshots of it. Again, not through Kubernetes, but you can always do things external to Kubernetes currently, right? One of the things that's coming, right, is with snapshots, you're going to be able to do that type of, hardware-based backup there, but you still would want to be able to, you can, do different ways. You can back up a file system, different things. So yes, you definitely still want backup as a primary thing here. Just because you're moving to this container world doesn't mean you're magically going to be protected, right? Backup is going to be very important going forward, and things are getting in place there. There's a lot of movement towards making sure backup is there.
Okay, and then the second question is, you mentioned Kubernetes a lot, but what is the status of native Docker CSI support? Can I use CSI for usage within Docker without deploying Kubernetes?
So Docker has the UCP, Universal Control Plane, I think is what it stands for. So, which is a unification of Docker Swarm and Kubernetes. The last I looked into Docker specifically, they were very much, they weren't open yet with, and again, sorry, it's been a year or two since I looked at Docker, but the last was there was only certain drivers that were allowed to be used in UCP. I don't know with CSI how far along they are with that. I know that's, because the idea with CSI is that, develop a driver once, integrate with that platform, and you can use it, right? A lot of what I'm doing right now is Kubernetes focused, so, that's why I talk about it a lot here.
Okay, fair enough. So let's go on with the demo because I want to make sure you get that done, and we'll come back to more questions at the end.
Okay, excellent. All right, so next thing I'm going to do, so I already created a storage class called Gold. So it's associated with a storage hole on one of my storage devices. So again, this time, I'm only going to create a persistent volume claim. I'm not going to create a persistent volume. So essentially what I am doing here is I'm going to show you dynamic storage provisioning with a storage device. So again, I have a persistent volume claim. I have a name for it. And then I have, the storage class name of Gold, which I already created, which is associated with a flex volume driver. I'm going to ask it to create a 20 gigabyte volume. So I'm going to click create here and let it go. So it takes a little bit for the user interface to get updated. But here. So again, I didn't have to do the persistent volume here. You'll see here, there's this PVC-UID that got associated and created. And when I come over here to my persistent volumes, see here I have, it's been bound and claimed, and the reclaim policy is delete. That's my default. I left it in the storage class. So essentially here, I've dynamically provisioned a 20 gigabyte LUN on my storage device. So again, I'm going to do a deployment here around making use of that persistent volume claim. And this time it's going to have to map the volume for me and stuff like that. But again here, so I have the deployment is going to use this volume, and the containers are going to use this volume and mount it here. And I'm just doing a very simple command where it's essentially just running forever. There's no actual application doing. This is just to showcase storage provisioning. So again, I can come over to my workloads. This will take a little bit longer because it does have to do the mapping and everything. So here's my deployment for a container, and it's working on spinning up here. So I'm going to let that go here because some of the other things I do take a while. So I'm going to go through, essentially probably go through 3 use cases here. So that was, me using YAML files to create storage or make use of storage, and then create a deployment to have that container make use of this here. So the next thing I'm going to show you is Mongo. So like I said there before, I essentially was just a dummy application that just, while true, just keep running, so it'll just always run forever, right? But, I want to be able to actually deploy an application here. So in this case, I'm going to show MongoDB. And I'm using essentially Helm charts. So this is, again, another thing brought by the CNCF. So this is essentially, if you can think of Helm charts, they're like RPMs in Linux or Red Hat or whatever, or, package manager. So it packages all the things that are required to make a application. So, you need storage, you need networking, so you need to be able to access a resource. So in Kubernetes, that's a service. And then it also needs the container, whatever it's doing here. So in this case, I'm just going to give a release to my Helm chart here. And I'm going to throw it in the default namespace. So namespace is a way of, you know, making it so that, you know, you can set, you know, you have your HR namespace, you have your finance namespace, so that, you know, they each have their own thing here. And as I mentioned, awesome thing about, you know, containers, I can run on it on AMD64, Power, Z. You know, all I have to do is compile it for that particular platform, but I don't have to do anything else, right? So, you know, write once, run many, anywhere. So here, essentially, this is where, you know, I'm going to tell it to do dynamic storage provisioning, which is the thing I did last time. If I didn't check this, I would have to create the persistent volume claim first. So I don't want to do that. I just want to let this thing do it. So I'm going to come down here in gold. Again, I'm just going to have it create a 20 gigabit volume for me. And it'll have this name associated with it. And I can tell it where to mount it, but I'm going to leave the defaults. And some other thing with Kubernetes, you can set resource limits. So I say you can't use more than 256 megs of memory. You can't use more than 100 CPUs with limits here. And as I mentioned, being a package manager, it's going to create a service that maps, so I can externally, so I can access this container. So I can spin up, you know, 10 MongoDB services all listening on this port, but from the Kubernetes perspective, it'll create a dynamic port that's available for it to use. And I can do different configurations, like, you know, I can set my database name, I can set my passwords, things like that. Just leave it default. So again, Kubernetes is really cool. You can, you know, it allows you to, you know, run a lot of different applications there. And Helm makes it pretty easy because you can, you know, essentially build an application that's available for use there. Let's go back and check on our deployment. Make sure it came online.
And Matt, we have 3 minutes, so.
Okay, so let me jump out of screen sharing and finish off here. All right. Okay. So again, I like to share information. So there's 4 slides with the demos I went through here. This is essentially the last thing I did. But then there's another one where you create the PVC first and you don't do dynamic at the Helm chart level there. But back to you, Michelle.
Okay, great. Thank you, Matt. That was really great and a very interesting demo. I want to, unfortunately, we're kind of almost at the top of the hour, so probably out of time to answer the couple more questions, but I want to let people know that we are going to post answers to all the questions later. So please stay tuned for that, and we'll be sending out a link to a blog with all the answers in them. So if you didn't get your question answered, make sure you look for that. Also, this is a webcast series. I wanted to remind everybody there was Kubernetes in the Cloud Part 1, which was discussed previously. That's available for replay. And coming soon will be Kubernetes in the Cloud Part 3. So stay tuned for more on Kubernetes. We really appreciate you attending today. Please, please, please rate this webcast and provide us feedback. We can only improve and get better and, you know, respond to what people are interested in if you write to us. So use the feedback from audience thing in the chat in this Bright Talk webinar, I should say. And we will have a full Q&A from this webcast, as I said, posted to the SNIA Cloud blog. You see the link there. This deck is being broadcast to all of you, so you can download the PDF for it and enjoy it at your leisure. So I want to thank everybody again for attending today. Thank you to the presenters today, Matt Levan and Tom Clark. You guys did great. And we'll see you all at the next webcast.